All right, we're doing number 64 notes. These notes are over the cubic and cube root graphs and transformations. I pulled this information way back from the notes on parent functions. I looked it up. It was notes number 9 from the first semester. So if you have notes number 9 from first semester, you can simply refer back to that. Put a sticky tab in your journal so it's easy to find. If you don't have notes number 9, then I strongly encourage you to copy all of this down again. The cubic, the parent function cubic, is denoted by some sort of function notation or y. I don't care which one you do. It's equal to x raised to the third power, pronounced x cubed. This is the parent function graph. I posted or I plotted these 3 points because those are the 3 points that are easiest to plot and to calculate. I made a table of those values. You plug in -1 right here for x, and -1 cubed means -1 times -1 times -1, what comes out to be -1. You plug in 0, 0 cubed is 0. You plug in 1, 1 cubed is 1 times 1 times 1. You plug in 2, and 2 cubed is 2 times 2 times 2. That comes out to be 8. I put a star right here by this one because I wanted you to notice that these 3 points are the exact same 3 points that we plot on the cube root function, which we know is the inverse of this function. Remember, the inverse is the one that reflects around x and y. So we switch the x's and y's, but interesting enough, if we switch all of these x and y's on these 3 points, we end up with the exact same 3 points. So the 3 points that make up the parent function cube root, or cubic function, is the same 3 points that's on the cube root. You need that 4th point that we have down here so that you can tell the difference. The 2, 8 is going to be on this. I plotted it way up here. It's not on that, doesn't fit on that piece of graph paper, but if you go over 2 and up 8, it's going to be right about there. That's going to be another point. And of course, -2, -8 would also be on there. And on this one, if you switch the x and y value, then the point that's on this one is 8, 2. And that's really what helped when you first see the difference between the cubic function and the cube root function, is that extra point. So you really do need to be sure and include those points. They both, the cubic and the cube root, have domains of all real numbers. Don't forget that if you're writing it in terms of an interval notation, it's -infinity to +infinity on all of these, here, 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 and here. Inequality notation, we don't generally write inequalities. Some people do. I do not. I have a hard time using the infinity symbol with inequalities because to me it seems redundant, but it's not going to include it though because you can't include infinity, so there should not be a bar underneath there. But you might see it written like this somewhere. I'm going to do this one for range. And then it would be to positive infinity. Again, I don't like using mixing infinity symbols with inequalities because, like I said, I think it's redundant. But there is no way to write all real numbers in inequality notation if you don't. You just have to use that symbol right there, all real numbers. So, the x and y intercept is at 0, 0. The end behavior is going to be different because it's a cubic. End behavior is going to be different because it's a cube root. We'll look at the exponent on this one. We'll see that it's raised to the 1/3 power. We know it has different end behavior because it's odd. Well, 1/3 is also an odd number. So it does have different end behavior. All of the transformations that we've already learned still apply. So I am going to give you examples of each one of these so that you can see it in both the cube and the cube root. We'll also be seeing the change of these ordered pairs. I may not do all the ordered pairs every time, but I will show you the change of the ordered pairs because that's what you're going to be expected to do on your homework. They are continuous functions because there are no gaps or breaks in them. You can draw both of these graphs without ever having to pick your pencil up. Once you start drawing it, you can draw it towards eternity without ever having to pick your pencil up. The maximum number of roots or zeros for the cubic function, you should remember, hopefully, that since it's a third degree polynomial, it has to have 3 solutions. So I put it's going to have 3 real ones, or it could have 1 real one. If it has 1 real one, then it's going to have 2 imaginary ones. That's the case of this one right here that we see. It's only crossing the x-axis once. It's a cubic, so we know it has to have 3 solutions or 3 zeros. Or 3 roots. So since it only crosses the x-axis once, this particular one means it only has 1 real one, the other 2 are imaginary. But it can have all 3 of them be real. A term that we're going to be using probably more in the next lesson than we are in this one, you also need to notice that this parent function, this cubic parent function, is a one-to-one function. Remember, the test for being one-to-one is the horizontal line test. We know it's a function because it passes the vertical line test. Anywhere you draw a vertical line, that vertical line is only going to cross this graph one time and one time only. The horizontal line test is used to determine if its inverse is also a function. Well, we have its inverse graphed right down here, so you can see that the inverse passes the vertical line test, so that means the graph up here passed the horizontal line test. Any horizontal line only going across this once. That one-to-oneness is not true for all cubic functions. I'll just give you a real quick sketch of one right here. There's a cubic function right there, and there it fails the horizontal line test. Except my horizontal line is not very horizontal. Let me see if I can straighten it up a little bit. My horizontal line, there we go. It still passes 1, 2, 3 times. This would be a function, but its inverse would not be a function. And so if we wanted to make sure that its inverse was a function, then we might have to restrict the domain to make sure it was anywhere so that it's one-to-one. So we don't generally have to restrict the domains because it's all real numbers. Both of them are all real numbers. But if you start having curves that take away the one-to-oneness, then you do have to start restricting domains. All right, so that was just a lot of talk, not a lot to do. So I'm right at 8 minutes. I'm going to go ahead and stop this video, and we'll come back and I'll give you some examples here.